We now have an invited speaker, Anais Möller, if I pronounce that right, like also from Swinburne, and she'll be talking about transient alerts and brokers, a perspective from the Fink broker.
Perfect. Thank you very much. I will share my screen now. Let me know if you cannot see it. Thank you very much for giving me the opportunity to speak today about transient alerts and brokers and our perspective from Fink, which is one of the brokers that will be processing the Rubin Observatory data. Now, before I start, I am in Swinburne, and I would like to acknowledge the traditional owners of the land where I work, which is the Wurundjeri people of the Kulin Nation. Now, with that let's start a little bit about Rubin and LSST. We have heard a lot about this immense survey that is coming up, that is going to give us so much data that we haven't had before from the ground in optical bands. So basically, we will be scanning the southern sky with bands coming from U to Y, so basically quite complementary to Roman. The idea is to image the southern sky with different programs. So there will be a wide fast deep, which will be the whole coverage of the southern sky. Then the deep drilling fields to have a coverage more in time than in area. And then there will be other surveys that are marked here in purple. Now, the observing strategy for each of these parts of the survey is not yet defined, so this will change with time, especially if you want to know the cadence between observations. But the idea is that the deep drilling fields will be quite frequent, and the wide fast deep should be around a week or maybe a little bit more, depending which colors are you searching for. Now, today I'm going to talk more about what can we do with single images from Rubin, what can we do with the stack images from Rubin. And the single images for Rubin, that is a 30-second exposure, are actually quite deep. And we haven't had this depth in the southern sky in such a wide area before. So we're talking from the Y22 magnitude in a 5 sigma point source depth to the G25, which is pretty good. So we will be quite deep in the sky. Now, Rubin and LSST, of course, have a series of data products. Basically, when you get an image from the sky with a wide field of view, it's every 30 seconds, let's say around 20 terabytes per night of images. Then there will be a prompt data product, basically something done like on the fly, that is a difference image analysis to actually detect those objects that are changing in the sky, transient events. And then we will have within 24 hours the images, objects, and source catalogs from the difference image analysis, and as well as the orbit catalog for the solar system bodies. Now, of course, if you have proprietary access, you will have access to all of these, as you need to wait for the annual data releases that will happen every year, and the last one at the end of the 10 years of LSST. Now, I'm going to talk today not about the proprietary data, I'm going to talk about public data. So it's data that we can all access, and this is exactly what the prompt data product is. So the difference image analysis basically detects things that are changing in the sky within a signal to noise ratio, of course, and it will communicate them automatically to the brokers, basically. So what does this transient alerts contain? So first of all, it contains a thumbnail, not the whole image, but a thumbnail of the science image that had this transient detected, the thumbnail of the template that was used for the difference image analysis, and the thumbnail of the subtraction. So this can help us to also determine how good the subtraction is, although there will be probably indicators, like there will be controls on real logos, of course. Now, from these, aside from the thumbnails, we get the light curve, so the observed luminosity through time from LSST. Now, this won't be only the detection from tonight, but it will contain the history over up to a year of this transient if it occur in the same coordinates. So basically, if in the same radix you have another transient that happened in the last year, you will have that light curve as well. So usually this is very useful to get for AGNs or microlensing events, etc., because you have long baselines. So this will be automatically sent within 7 seconds of the exposure being read completely, and it will send around the world. And we expect around 10 million transient alerts per night, which is a huge data volume if you think that every night for the next 10 years, we will have 10 million alerts per night. And the big question here is, how do you go from that number of transient candidates to something that we can do science with and something that we can actually trigger follow-up or connect to other data sets? So that's how the Rubin community brokers came to place. The idea is that we are platforms that we will be able to ingest those 10 million alerts per night, actually process them, enrich them, also filter them for different science cases, and then communicate it with the community. Now, the process worked like this. In 2019, we had a call of intent of groups that wanted to do a broker. There were 14 groups sending letters of intent. And after a lot of work and a committee deciding which brokers will be selected, the decision was made in August 2021 to choose for 7 full stream brokers. What does this mean? These 7 brokers will receive the full transient candidate alerts every night directly from the Rubin project. So we will have a connection directly there. And we will do this enriching and processing and try to filter for as many science cases as our community is interested. Now, I just showed you here a map of the brokers that have been selected. We have Alerce in Chile, we have Antares, Bebamul, and PitGoogle in the US, and we have 3 originally from Europe, Laser, Ample, and Fink. Now, I also put Fink in Australia because I'm in Australia now, and we are 3 PIs, so we are around the world. If you have questions about like the architectures and fundamentals of the brokers, I'm putting below some of the references. I'm not gonna aim to explain all of the differences between the brokers. The similarities is that we are all gonna receive the same alerts. We're gonna process them differently with different technologies for science cases that can be overlapping or quite different. So for example, some of these brokers have been only prototyped. Some of them have been developed for CTF. Some have been applied for CTF, and some have been scaled for LSST. So we are very different from the beginnings of our construction. Now, of course, it doesn't mean that we don't talk between each other. There's a big collaboration between us. For example, we have a huge collaboration with Alerce in the structure side, how to become more robust for LSST data volumes. With the European brokers, we're constantly talking about how we can actually better use resources like TNS or cross-matching catalogs or machine learning frameworks. So today I'm going to tell you more about our experience as Fink, as an example of what we can do with a Rubin broker and Roman. So what is Fink? First of all, it's not an acronym, which is rare in this field. It's a community effort, so it's open to anyone. We believe in open source data and open source code, so everything we do is very transparent, so we don't use proprietary data. We're a community of 40 researchers and engineers, and I think it's important to highlight the work behind the scenes of a lot of technology that we are using. We're experimenting with things like even graph databases, which is very interesting. Of course, we designed Fink to process Rubin big data. So we are in distributed computation. We have a lot of technology behind that actually makes us to be able to process the 10,000, 100,000 alerts in real time, basically. And because Rubin is still not there, we are now processing the CTF2 public alert stream, which is now available at the finkportal.org. So you can take a look already how the processing is done and what can you find from CTF. Of course, CTF is not Rubin, but it's still a very interesting survey in the sense it's a very wide field covering a large area of the sky and having a lot of interesting data on transients. If you're curious about the architecture and first science results, we have our first publication in 2020. I highlight the name of Julian Peloton, who is our infrastructure lead, and Emily Ishida, which together with me, we are the leads of Fink. And one thing that is interesting for people who are doing proprietary data with Rubin is that we'll be deployed. Actually, we already have we're starting to deploy actually in the supercomputing center in France, where half of the LSST data will be processed. But of course, this is not something that you need to have access to in order to use Fink. So let's go now to the details that you all want to hear about how we process transients. So this is what I call Fink in a nutshell. Basically, when we talk about 10 million transients alert per night, it means around 10,000 every 37 seconds. So we will receive this. The first thing that we do is to make some quality cuts. If you have ever used difference image analysis, you have bogus events, so artifacts from difference image. We eliminate those. This is right now for CTF is 20-30% of the stream, which is quite big, but it's reasonable. We expect something similar for LSST. Of course, as I told you, each broker makes different quality cuts, so we are not all processing the same way the alert. So what do we do in Fink once we select the alerts that are not bogus? The first thing is that we do a positional cross-match with the coordinates. One way of doing it is using catalogs. So we have a link with the CDS Simbat service. So to know if this transient detected in CTF or Rubin is a non-variable star, or maybe contextual information, it has a known galaxy close by with this redshift, or maybe you don't have any information in a catalog, but this is something important to know. Then we also do cross matches with VO events and GCN notices. Like for example, if LIGO Virgo has a gravitational wave footprint, we can actually tell you, well, all these transients are within this footprint. We're also doing dynamic catalogs with GRBs, like with Swift. And this goes very fast. So we just like to do the cross match to see which events could be in that footprint. Now, aside from just cross matching, there's other things that we can do. We have the light curve information and the thumbnail information. So we do what we call Fink features. So basically it's a magnitude rate, if it's increasing, decreasing in magnitude, what is the color? Is it achromatic? How does it change with time? Maybe the thumbnails, what type of morphology you have, all of that. These are things that we're working towards also supplying. And a big part of Fink is also to use machine learning classification to actually provide a probability of this object being a kilonova or a microlensing event or supernova, and adding that information into the alert. Now, with all that information, with the cross-match, the features, and the machine learning classifiers, you can actually customize filtering to receive only the events that interest you. Like if you're only looking for rising events that are achromatic and have this slope and have a machine learning a score of, I don't know. So you can choose that. Now, there are two ways of accessing this type of filter streams. So one way of doing that is through the real-time API, which is basically automatic. Within a minute of being observed in Rubin or CTF, you can actually have that data, which is ideal for robotic follow-up of objects. Then, of course, there is a more human-friendly way of doing this, which is the Science Portal, a web page, or a REST API, which is a fancy way of telling you you can actually query out database from your Python notebook or your terminal. To give you an idea with CTF, we signed an MOU in 2019, and since then we have received 120 million alerts. This is very interesting because if you think about it, it's only 2 years ago, and it's CTF, which is much smaller, imagine for LSST. And right now what we're doing is that we're splitting and filtering those alerts into different streams like supernova, microlensing, variable stars, etc. Now, with all that in mind, and there's much more than we can talk about that, how can we work with Rubin and Roman? And where is the role that the brokers can play here? So the first thing of all is that we will have public photometry. So it's a difference image analysis. So it's not seeing modeling photometry, which for cosmology sometimes we need. But if you're searching for a transient and you want to see if there is photometry in other wavelengths that are not Roman, this information will be available. Not only will it be available through like a cone search, but you will also have information on context, like the host galaxy maybe, some features of the light curve in the optical, etc. So this is something I think all the brokers we actually supply. The second thing that I think is very important is detecting early transient candidates. So when we detect a transient, maybe we have a couple of observing epochs, and this is actually quite big because it's a week, over a week. But one question that you can ask is, shall we trigger a spectroscopic follow-up or photometric follow-up? Should I do a TO to target these? But first you need to know what could it be? What type of, is this interesting for my science? So one of the things that you can do is, well, trigger spectroscopic follow-up, but we all know that spectroscopic resources are limited. So maybe you want more information on what this object, is it promising or not? Also, the time window is quite important. You want to actually trigger this follow-up early so you can have your transient on peak, in particular for super fast transients. But for supernova, for example, you have a window of a couple of weeks. So you don't want to wait till the object has faded away. So I think this is something interesting with Roman, especially with kilonova. I think we saw this plot yesterday showing the R band in LSST and the H band in Roman, and what will be the observer time frame coverage with the redshift limit. And you can see that the R band in LSST is quite powerful, especially at high redshift, and is quite complementary with Roman. So we could actually select kilonova candidates and see if there is the data in Roman as well accompanying that. So in Fink, we already have some ways of selecting kilonova. So we have some machine learning classification scores, some magnitude rates that we use to actually select kilonova candidates. And also we have another method that is cross-matching with host galaxies that are close by. This is something that we work with the Grandma collaboration to trigger follow-up. And there's a paper in preparation with some of our results. But of course, if LIGO Virgo is online, we will also do in real time the cross-match. And I'm missing Kagra because it will be soon also online. So I think this is important because for one side, we have the LIGO Virgo footprint cross-match, but we can also do something completely independent that doesn't need them to be working, which is something that Gilai, I think yesterday mentioned, that is very important to find kilonova, just without the gravitational wave detection. Now, science that is close to my heart are supernova. One of the things that we can find is to detect early supernova candidates. So we have 3 machine learning classification methods implemented right now, including one that has active learning that I'm going to mention at the end, which I find very interesting. What we're doing is that we combine these machine learning scores to select events that are promising supernova, together with some selection cuts. And we have implemented an automatic bot that reports this event to the Transient9 server, TNS. And there we get a name for the transient, but to give you an idea how good these filterings can be from the CTF data, in the last year, we reported around 900 events. From these, 552 were spectroscopic confirmed supernova, and 1 was not a supernova. The rest was not follow-up spectroscopically or didn't have a classification. But I think this gives you an idea how you can go from these huge data volumes and then select a subsample that is interesting for your science, and actually with partial information, because this is quite early. In average, we sent it 7 days before maximum light for a supernova. So of course, this goes beyond supernova and kilonova. We have projects with GRBs, for example, to report in real time candidates. And this is something that we're doing with the Colibri team as well. But there are other transients that we're working with, like neutrinos, cross matches, fast transients, supernova. We have heard a lot of per instability supernova. We have a new model that we're working on that. and finding the weirdest things that we can find. Of course, not in real time, but if you're interested in triggering follow-up, you can do that with the TOM toolkit, which we have an integration for. So aside from photometry and early transients candidates for follow-up, I'm going to talk about another thing that is getting large samples without spectroscopic classification. So I think this is something that is becoming more common nowadays. So basically you have a light curve, the transient has faded, and you want to select a sample of transients. And what you can do is to get a classification probability, for example, use a threshold and some selection cuts and actually get a large sample. Now we're doing this for type 1a supernova cosmology. And for example, for the dark energy survey, we just did it very recently with actually the machine learning code that is implemented in Fink, supernova. And we can see that the accuracies of those classifications is over 98%, and the contamination for the cosmology grade type 1a supernova sample is around 2%, which is quite good because if you think about a spectroscopic misclassification, we're on this ballpark. This is super important and it's continuing to be something that is being investigated. I think Helen Q on the first day actually talked about this. But to give you an idea of the power of doing photometric classification, aside from spectroscopy one, this is a plot from the dark energy survey 5-year sample, type 1a supernova sample. And you can see the redshift distribution of the spectroscopically confirmed type 1a supernova against the photometrically confirmed type 1a supernova. And we're going from a sample of hundreds to a sample of thousands, which is covering a larger redshift space and population diversity. Now, this blue sample was classified with light curves and host galaxy redshifts. But if we go a little bit forward and forget about the redshifts, we can actually get even larger samples. They have their biases, which is something I'm working on right now, and we can discuss about this. But you can see the power of getting photometric samples. Now get these with Rubin, which will be a much bigger survey, plus you can get these samples, plus the photometry of Roman, then you can characterize type 1a supernova for better calibration and intrinsic properties. Or you can do this for any transient that you can think of. So we can go beyond our current samples with a very rich data set. Of course, I cannot tell you everything that we're doing in Fink right now. There are people working in microlensing, finding solar system objects, parent stability, fast transients, the most anomalous things, and also how to optimize training sets for supernova classification with methods like active learning, which I think Ryan was mentioning earlier. Now, because these training sets are always our limitation for us. Now, I hope in this talk, I have given you a little bit of an idea, what is a broker, what can we do, and how important it will be to use a broker for Rubin. We cannot do 10 million transient candidates by eye every night, and especially if we want to take advantage of the synergies that we can have between Rubin and Roman, we cannot waste our time just trying to come through the haystack. Now, a way to come through the haystack automatically, as I have shown you, is Fink. We are quite fast. We process basically in real time data volumes as Rubin. We're already deployed with CTF, and we have already some models working for filter stream. Of course, there's always more to do. So this is depend on the community. If you're interested in something, we can grow and make it work. I think transient science can only gain between synergies between Roman, Rubins, and other multi-wavelength emission their surveys. We will have complementary information from photometry to detections. We will try to find these counterparts, whether it's an FRB, GRB, gravitational wave event. I think the brokers can provide also information already automatically digested on the context of the transients. It can give you early classification so we can coordinate follow-up with other facilities, especially robotically, because I think we will have such a big data volume and some transients will be so time sensitive that will require that. So with that, I stop. I'm more than happy to answer any questions, but please, you can contact us anytime through this email as well. Thanks.
Thank you so much. We have a couple questions in the Slack, but I have to ask, what is the acronym GRANDMA for? That's the best acronym I've seen in a while.
So it's what is it? It's I'm enthusiast of gravitational wave. I never remember. It's a fun acronym. It's true.
Okay,
I will have to Google it because I cannot recall right now. You got me in this spot.
Okay.
I know it's addicts.
Oh.
It's addicts, I think.
Maybe it's not an acronym. I don't know about that.
It's an acronym. It's like
has to
people
be.
super enthusiastic with the gravitational events around the world. It's something like that.
Great. Rangachari asks, in terms of aerial coverage and timing, Euclid and Rubin are much more closely matched than Rubin and Roman.
Yes.
Is there a plan to integrate an interface with the Euclid archive into Fink?
Yes, this is something into discussion because Euclid is proprietary at the beginning. So we will have to wait for the data releases, but we have right now discussions on what we can do as a synergy. In particular, I think for time domain science, having the redshifts that Euclid will obtain will be quite complementary. But this is something that we're working on. But if you're interested, more than happy to have more people on board. As I said, this is all a community effort, and we're trying to make it even more, reaching more science cases and surveys.
Great. Sebastian Gomez asks, how does Fink do the host galaxy association for each transient? Or how do you define a close by galaxy?
So right now what we're doing is very simple. We just do a cone search and we just search within a radius how close the galaxy will be. We have some projects to actually use the redshift, if available, to actually do a luminosity distance ratio, which we use a lot in supernova, but this is a little bit hard depending on the volume and the transient that you're searching for. So this is something that is still in progress. But right now what we do is very simple. Radius, find the closest galaxy.
Great. Monica Sorisam asks, can you comment on your real-time API to access the filtered alerts? Are you using streaming technologies?
Yes, we are using Kafka streams. So it's the same type of technology that we use, that CTF or Rubin will use to send the streams. For the automatic stream, like the robotic follow-up in real time, we use Kafka. Now, there are other ways of obtaining this. We implemented for Grandma actually a TNS bot. So, sorry, a Slack bot is called. So we just ping the event into a Slack channel. So if that's something that you're interested, we can do an email, Kafka stream, Slack bots. I'm sure that we can find other ones if you're interested on.
Well, thanks to Jeff, we now know that GRANDMA stands for Global Rapid Advanced Network devoted to the multi-messenger addicts. It's amazing. I would like to join this group.
Yeah, it's a very good acronym. Thanks, Jeff.
Excellent. Any other last questions? Great. Well, thank you, Anais.